we started the discussion on thin film deposition, right? So we'll continue that discussion today. It's going to be a slightly longish module because we have a variety of thin film deposition techniques that are used for VLSI manufacturing, and it's also very important from various other applications like sensors, photovoltaics, and so on and so forth. So we were discussing this, that you have a source of the material that you want to deposit, right, and then gets transported. So it has to be vaporized and then gets transported, and then you have a deposition that is happening on the surface of the final substrate where you want the film to grow. And then on the way you do a lot of measurements to actually study the actual process, how the growth is evolving, right? And you want to control the temperature, the thickness, the composition of the material, and so on and so forth. So you actually may do what is called in situ measurements, but also after the film is deposited, you need to measure the thickness, refractive index, and various other parameters of interest. For example, you may want to look at the sheet resistance, you may want to look at the carrier concentrations if it is a semiconductor, and so on and so forth, right? And you may do a lot of physical characterization to look at the morphology, whether the film is closed film, what is the surface morphology, right? You want to look at the roughness, for example. Yeah, so these can all be very important things. And then, of course, for certain applications, if it is, let's say, if it is a metal, you want to look at the work function of the metal, and if it is a dielectric, you want to look at the dielectric breakdown strength, the interface between the dielectric and semiconductor, and so on and so forth. So you will actually do a lot of characterization, which is a very important component of the research and development. And of course, in manufacturing, you would monitor all these, not all things of interest, but at least some of the parameters like thickness would be monitored very routinely in manufacturing also. Now, if you look at a PVD conceptual system, so very simple. So you have a chamber, okay? It's a vacuum chamber, and you have the substrate on which you want to deposit the film, okay? And then the source of material to be deposited, and you provide some energy. So we'll see different source of energy, and from the source you evaporate the material, okay, and then it gets transported through this space and get deposited on the substrate, okay. Now the source of energy can be, as we discussed yesterday, can be thermal, so you heat up the source. So it can be resistive heating, for example, right, Joule heating, or you can have electron beams for heating, laser pulses for heating, and so on and so forth. So you have then different types of evaporation processes. So usually when you do a resistive heating, that's when you call it as thermal evaporation. Yeah. Otherwise, you call it electron beam evaporation if you are using electron beam, laser based deposition if you are using lasers. You can actually use ions and so on and so forth. So now the high energy ion. So you usually create a plasma, right? And that is used for sputtering. The source, or you can actually create ion beams, okay. There is a difference here because this would actually contain ions, electrons, and excited radicals and so on, but this would be purely ion beams. Okay. So from the measurement side, you would look at the purity of the source, vacuum measurements. So what is the vacuum condition? For example, film thickness, composition, interface, and so on and so forth. So this gives you a bit more detail. Okay, so you have a vacuum chamber, yeah, and you have pumps to actually create the vacuum. It can be single stage, double stage, depending on the vacuum requirements. And then you have the sources, so this can be the sources, right? Different types of sources. And this is your substrate. And you can actually do a thickness monitoring by many ways. One of the technique is to look at the resonance frequency of a quartz crystal, okay, and that depends on the weight of the crystal, and as you deposit material onto the crystal, right, its weight is changing, so its frequency will change. Okay, so you have a rate monitor which is next to the substrate on which you are depositing the film. So the film will also get deposited on the rate monitor. Okay, so the weight of the quartz crystal changes and its resonating frequency changes. So you can electrically measure what is the resonant frequency of the quartz crystal. And the sources can be different types, so depending on the type of system that we are talking about. And you use this kind of systems for deposition of metals and metallic compounds. Dielectrics can also be deposited, but most of them, or actually many of the dielectrics of interest in semiconductor applications, like silicon dioxide and so on, the melting point is very high. Okay, so you don't usually use these techniques. Molecular beam epitaxy is a very common process for semiconductors. Now you have a vacuum system. Okay, so this concept of mean free path is very important. Okay, so that's something that you are trying to control by setting a vacuum condition. Yeah, so mean free path, this idea is probably known to you. So if you have a gas, right, the gas molecules are moving around randomly, and mean free path is the average distance between collision events between the particles in the gas. So we'll just look at this equation, but more importantly, what are the values, typical values you find in vacuum systems used for semiconductor processing. So that is interesting for us. So this is the mean free path, and you see these different parameters. So Kb is the Boltzmann constant, T is the temperature in Kelvin, and P is the pressure, okay, in Pascal. Sigma is the collision cross section in centimeter square. And you can see some typical values for sigma. So 4 × 10⁻⁻15 centimeter square. So essentially, you know, it's not necessarily a head-on collision between particles. Even if they pass by because of Coulombic interactions between electrons, for example, that can result in a scattering of the particles. Okay, so you are actually talking about what is the area. If I have a particle and I am looking at it this way, what is the area of influence of this particle, right? Yeah, another particle passing by may actually experience a force from this particle. So what is the cross-section area for this interaction? So if I now plug in these values for atmospheric pressure at room temperature, so that is 300 Kelvin, so the mean free path is about 70 nanometers. So you can see in air, every molecule that's moving around would actually undergo collision within 70 nanometers, on the average. Okay, so that's very small, right, number. So they actually collide very frequently. Now, in an evaporation system, one of the requirement is that the mean free path should be much larger than the chamber dimensions. So this is because you have a source and you are evaporating, right? And if the particles undergo a lot of collisions, they will actually lose the energy. Okay? So they may actually not get transported. Okay? So this is a possibility. And also they actually may get contaminated if you have oxygen. For example, I'm trying to evaporate aluminum. So on the way, if it actually collides with oxygen molecules, they may react and form aluminum oxide. Okay. So the quality of the film, eventually what I'm looking for is deposition of aluminum, but I may end up depositing aluminum oxide instead, right? If I have a bit of oxygen, too much of oxygen, and the aluminum particles collide with the oxygen. So we need to, then you would, let's say you deposit a thin film of aluminum and you look at the resistivity of this film or sheet resistance, that would be fairly high. Yeah? So the quality of the film in terms of the resistance and other properties that you target may not be met. Okay? So we need to evacuate the chamber, and you can see these things here. So in thermal evaporation system, the pressure is in this range 10 raised to minus 3 to 10 raised to minus 6 Pascal. This is another unit of pressure, so you can do a conversion. And the mean free path using the equation works out to be in the range of 7 meters to 7 kilometers. Okay? So this is a thermal evaporation system, not very high vacuum conditions. So the chambers used for deposition will not be, how many of you have seen or used thermal evaporation systems here in the labs? How big is it? Maybe half a meter, right? From the source to the substrate. Okay? Half a meter is maybe a bit too much. Yeah, but that gives you a sense. Okay, so here we are talking about mean free path in the range of 7 meters to 7 kilometers. Yeah. So at the lower end of the pressure, it hardly ever goes through any collisions. Okay. Now, if you look at molecular beam epoxy, you go to the extreme vacuum conditions. So if you look at this less than minus 10 raised to minus 9 Pascal, the mean free path is greater than 7,000 kilometers. Okay, so again, molecular beam epoxy systems, if you look at the distance between the source of the material and the substrate on which you deposit the film, would be few tenths of centimeters. Yeah? So this is a very important thing to keep in mind. So this means that in an MBE system, the particles that are ejected from the source hardly ever goes through, never goes through any collision before they meet the substrate. Okay, very important. And in fact, it's very high vacuum, right? Very low pressure, which means that there's hardly anything inside the chamber. Yeah? So you get pure materials deposited on the substrate Of course, we are assuming the source itself is highly pure, okay? And the substrate can be maintained very clean. So that's the next point that we would discuss. Now, how many atoms, if let's say I have a silicon wafer, I keep it here, or let's say I take my hand, like how many atoms are striking my hand? Because we mentioned that these molecules in the gas are moving around randomly, so they must be all, meaning a lot of them would be hitting my hand, right? How many of them per second are hitting my hand? Okay, so this is the flux, right? How many atoms are essentially incident on this area, right, per unit time. Okay, so that is given by this equation. So you can see again the parameters. Here the T is the temperature, P is the pressure. So higher the pressure, you expect more particles to strike, right, a given area. And m is the atomic mass in AMU. So you can of course use the kilogram, but it's already worked out. So m in this particular case is AMU. Okay. So we can then work out some of these the numbers for typical vacuum conditions you encounter in physical vapor deposition. So for example, nitrogen, yeah, so the mass is important. At 10 raised to minus 2 Pascal, the flux is 3 into 10 raised to 16 per centimeter square per second. Now this probably does not give you a sense, okay. So you are saying that, okay, every second if I am looking at, yeah, I keep my hand somewhere, right. So this is already a vacuum condition. So I would have very large number of nitrogen atoms, or meaning molecules hitting my hand at room temperature. But now, in the context of deposition on a substrate in a vacuum chamber, so the surface density of atoms is in this range. Yeah, it varies a little bit here and there, depending on the material you're talking about, and also depending on the crystal orientation and so on. But this is some typical number. So you can now realize that at this pressure, about 60 atoms strike one surface site. Okay, that can be an atom, right? Atoms or molecules strike the surface site per second. Okay. So if the atoms or molecules that are striking the surface stick to the surface, right, as they hit, yeah, then the surface will be covered in less than a second. Okay. So this is a very important consideration, because you can see, this is why when you do semiconductor processing, right, you clean the surface. Very important. If I want to grow, let's say, a very high quality oxide, right, the surface has to be cleaned. But then I take this wafer out. Yeah, I'm walking in the clean room with this. You know what is happening, right? Okay. So if I am looking at extremely, meaning, or very good quality interfaces and so on and so forth. So in VLSI manufacturing, large volume manufacturing, where the yield is very important, okay. So they have complete vacuum systems. Yeah, you have seen this movie, right? Global Foundries is something, one of the first lectures that I sent you. Do you remember how the wafers were transported? Do you remember? Between tools. So go back and watch the video again. Okay. So these details are important. Okay, now you can see this in MBE, yeah, under base vacuum conditions, 60 atoms strike one surface site in 10 raised to 7 seconds. You reduce the pressure, right? Okay. So this means that if I have an MBE system and I clean the wafer and load it, but still during the process I miscontaminate the surface, so they do some in situ cleaning in MBE systems, but then you can retain the pristine surface for very long time. Okay. So that's very important for many applications. Okay. So I think the last point we already discussed. Now the sources can be very simple, complicated, and so on. So you have maybe a tungsten wire, right, and 2 electrodes, and you pass a current to heat this. So this is like the old incandescent lamp, right, where you have the filament, and then you hang these pieces of the material you want to deposit. So it can be aluminum wire if you want to deposit aluminum. Okay. Or it can be a boat-like structure. So this material can be graphite, boron, nitride, and so on and so forth. Meaning this will be typically graphite. If you use a dielectric or ceramic, you will have to make an arrangement for heating it. Okay. So that's what you see here. And you place pieces of the material you want to deposit. This is more complicated. This is called an effusion cell, used typically in MBE systems, and where you can see this. So this is your crucible in which you load pieces of material you want to deposit. Okay, and usually in MBE systems, okay, so this is a complete vacuum attachment. So if I want to change this, then I need to open the MBE system. Okay, and as I mentioned before, to get the vacuum conditions required for good quality film deposition in MBE, it may take several weeks, if not months. Okay, so you don't want to change this, so it has to be then fairly large. Yeah, these systems may be after a couple of depositions, you may actually change the source. So you have a crucible, and then you have a heater, right? So this can be a ceramic, for example, the crucible, and you have a heater, so it can be carbon heater or graphite heaters, or other metals can be used. Then there's a shield to protect, the escape of heat into the chamber, right? This will be part of the chamber. And then there's the protective case, thermocouple to monitor the temperature, and this is a vacuum flange, so which you can attach to your MBE system. Okay, and of course you have cables coming out for the power. Yeah? You need to provide electrical power to heat this, and also you want to measure the temperature, so thermocouple cables will come out. Evaporation temperature depends on the melting point of the material. So these are the evaporation temperature that is mentioned here is actually the temperature at which the vapor pressure of the material is 10 raised to minus 2 torr, and it's very obvious that actually it goes up as the melting point of the material increases. Okay. So you can see the problem is that I may find it extremely difficult to deposit tungsten and similar materials, right? It's very easy to deposit aluminum, will be somewhere here, okay, and silver, gold will be somewhere here, 4,000. So gold is here, copper, and so on. Yeah, chromium. So these are things that you find in the lab where people do a lot of deposition, titanium, platinum also, chromium and so on. And this part is a little less, yeah. So if you want to deposit this, then the process of preference is sputtering, okay, where you don't have to melt the material, right. So if I want to deposit tungsten, I need to find a crucible which can hold it, okay, that's the problem. Okay, electron beam evaporation, this is an interesting process, and you're trying to solve some problem. If I have, let's say, a thermal evaporator where you use resistive heating, okay, you have a boat, right, in which you place your material to be deposited, and you want to melt it. So let us say I have a graphite boat, then I am placing aluminum or gold in it. What will happen? So the graphite has to heat up, okay, and of course you will get the aluminum will melt and it will evaporate, but if the graphite quality is not good, right, some carbon would also get deposited along with this, okay. So this becomes a problem, and E-beam evaporation technique actually tend to, or it's kind of a solution to it. What you have here is an electron gun, and you get an electron beam, right, and you can manipulate the electron beam using an acceleration voltage, okay, that gives the energy required, and then you can bend it around using magnetic fields, right. So here you have a crucible, and I place the evaporant, so the source here, and then I'm actually, the electron beam hits the source. So I'm not directly heating the crucible. I want to heat the source, right? The material I want to evaporate, I want to melt it, but in this case I don't heat the crucible intentionally, okay. I can, if I want, I can actually place or flow water to cool this. That is possible, yeah. So this means that the contamination from the crucible can be controlled much better in an electron beam evaporation system compared to a thermal evaporation. So the power density can be very high. You need to focus the electron beam, and you can use different acceleration voltages and so on for this process. So now the good thing is that you don't need a crucible that can withstand very high temperature, okay, because I can cool it very efficiently. So this means that high melting point materials can also be evaporated using this process. Okay. Now you can see sorry about this. So here you can see two films, okay, this is deposited by thermal evaporation method, and this is electron beam evaporation. Both are aluminum. So any difference, can you see this here? What are these actually? Pardon? This is aluminum, okay. What do you see? It's not looking very smooth, right? What are these things? Yeah, these are crystal, small crystallites of aluminum. This is 1 micrometer, Okay, it will be maybe 100 nanometers, something in that range, right? And what else do you see in these images? What is this? Pinholes. Yeah. So there are a lot of pinholes in this thermal process, and you can do a chemical analysis of the films, and you find in this case a little bit of carbon coming from the graphite. Yeah? So unless you pay a lot of money to get very good quality graphite, you can get a lot of carbon in the film. So as a consequence, the thermal evaporated aluminum would have typically higher resistance. Yeah. So for many applications, it is not acceptable. Okay, another deposition technique that is used not very widely, but this helps you to deposit some very specialized materials. And we have actually, I think, 2 systems in the lab. Both were designed by Professor Pinto, who was with us till about 3 years ago. Now he is a faculty member, and he's retired, but he's actually still working with an engineering college in Mangalore. So what you have is, so this is actual photograph, right? And you have vacuum chamber, so that is this thing here, right? And a laser source, okay? And this is your target, and this is a substrate where you want to deposit, okay? So you have a laser beam that is actually incident on the target that you want to deposit. So the laser beam will be focused, and as a consequence, the power density there would be very, very large. Okay. So this actually gets evaporated spontaneously because the power density is so large. The local temperature will be fairly high, and it's very interesting. You see that here. So material get ejected from the target surface and get transported to the substrate where you want to deposit it. Okay, but the particles inside actually have very high energy, so they will be excited and emit light. So that is what you see here. Yeah? This is what is called the plume, and this is not the laser beam. Laser beam is actually hitting here, but here this plume of highly energetic particles. So they get transported very fast through the system, and it is used for depositing very complex materials, like for example, so you can see the power density, very high speed, they get transported. So in a fraction of a second, the particles will be already on the substrate. Okay, this is the speed, typical speed. So there is no time for decomposition. They actually the laser hit the target, and in no time they are on the substrate. So you can deposit materials like this, which if you heat them, like in a thermal evaporator, right? Slow heating, and try to deposit, this would actually decompose into yttrium oxide, barium oxide, copper oxide, and so on and so forth. Okay, so this is, for example, this material find applications in high temperature superconductor kind of things. Okay. This is also interesting and for research, right? Here you have 3 metals and oxygen. So this opens up a lot of possibilities for what? doing permutations and combinations of periodic table essentially. Okay. So you have a pulse laser deposition system, and for a material science person, this is where you can publish papers, right? The whole periodic table can be mixed and matched. Okay, now how does the film growth proceeds? This is, was not very important from application perspective unless you are looking at very specific cases. But now we would be interested in extremely thin films. Okay, so this stage of the film growth is very important. So what happens is, this is your substrate, and you want to deposit the film on the surface. Okay, so you have the materials or the particles of the material you want to deposit coming onto the surface. Okay, and they can get adsorbed on the surface. So we'll discuss this process. So it can be a physical adsorption, where the particles are attached to the surface by weak van der Waals forces, okay, electrodynamic forces, and they can diffuse on the surface, yeah, because they have some energy, right? And also you may actually heat the substrate, so they can move around on the surface, and this movement will be random. Okay, so many particles come and hit the surface, and then they're moving around. And they can meet, right? And then at some point, some of them can get dissolved from the surface. Okay, and maybe multiple particles can come together, attached to each other. So this process is called nucleation. Okay, so once a nuclei grows, it cannot move as fast as the individual particles. Yeah. So once it nucleates, then it cannot move fast, but then other particles will then start and come and attach to this. Okay. So this is how the film grows. Now, is this just a theory, or can we actually observe it? Okay. So that is something we'll see soon. And now, if you look at these processes, I can probably control the surface diffusion by providing energy on the surface, right? And I can control this by making the surface more clean, and so on and so forth. Okay. Desorption is not a very desirable process if I am trying to do a physical vapor deposition. Let's say I want to deposit aluminum, and only aluminum is coming and hitting the surface of the substrate. Desorption means lower growth rate, right? I'm losing some material. I don't want that. But this is a very important process in chemical vapor deposition, where you may have a reaction, chemical reaction happening on the surface. So many of the byproducts that are produced due to this chemical reaction have to be removed. Okay. So the desorption is a very important consideration in chemical vapor deposition. And I can stop this process at the nucleation stage to make nanoparticles. Okay. So that is a very important application. Of course, you have the growth happening. So if I want, let's say, quantum dots and so on and so forth, right? This is a very important stage in the growth of the film that you can play with. Okay, so this we already discussed. Okay, so in the film growth, we mentioned about this interaction between the incoming particles and the substrate. Okay, so this is a graph where you show the interatomic distance that is between the surface, atoms on the surface, and the incoming particles, right? So here the distance is very large. So this is actually not on the surface, and the particles have not started interacting with the surface. But once they start interacting, you can have the total energy of the particles coming and the surface can decrease. Okay? When they come too close, of course, the repulsions between the particles because of electron repulsion can actually take over. So you have what is called Fize's option. In this case, it can be weak van der Waals forces that attach the particles to the surface, which means that I can if they come closer, then the energy can increase, and this can result in desorption of the particles. Okay, if the energy on the surface is higher than the energy away from the surface, the particles tend to desorb from the surface. Okay. So you have different conditions. For example, this is a dimer, which means that you have two atoms, okay, coming on to the surface, and it gets physisorbed. But here is actually single bonded dimer. So this is a very strong bonding between the atoms. But here it is actually a weaker bonding. So it might happen that on the way it actually decomposes on the surface, and then chemically react with the surface atoms. Okay? So then there is a chemical bonding with the surface atoms, and that is stronger compared to a physical attachment by weak van der Waals forces. So this can result in a lower energy. So the deposited film would make bonding with the surface, and the film would be more stable. Okay? And this is a stronger thing where you have already broken the dimer. So these are single particles like atoms, and they can get much easily, meaning if there is a chemical reaction, can be bonded very strongly onto the surface. Now there are processes like where you have a double bonded dimer coming on the surface, but then at some point if you provide surface energy, right, this can break and then goes into a chemisorbed state. So these things can be controlled in deposition by controlling the temperature, or if you're using plasma, okay, I can actually use particles in the plasma. For example, if I have argon, okay, argon does not chemically react with the substrate, but it can bombard the surface, right? So let's say if I bring in a material that I want to deposit on the surface, right, I get a dimer of this material, but then argon ions break this into monomers, for example, right? Or they actually transfer the energy, so to the monomers, for example, then they become active, energetic radicals, which can then react very easily with the substrate. So these are possibilities where I can control this, okay, different reactions. Now the reverse process is actually, so you can, control the whole deposition process, nucleation and film growth by providing energy on the surface by various means. Yeah, thermal energy, we can provide energy from plasma, accelerated particles, and so on and so forth. Please switch off your mobile phones. You can actually break the chemical bonds and absorb it by various techniques, and that can actually lead to chemical bonding, right? This is what we discussed. Okay, desorption is the reverse of absorption, and if you provide extra energy, again, the particles can desorb from the surface, and that can lead to then lower growth rate. So some of the cases you may actually want to have a low growth rate, okay? So it may be possible that you actually reduce the growth by facilitating conditions which will enhance the desorption from the surface. So you have seen this energy required for desorption can be provided by thermal energy, exothermic reactions on the surface which release energy, right? or from plasma, fast moving particles. Okay, this is something we have seen. You have the film growing by nucleation, right? And if you now measure the film thickness as function of deposition time, you don't find a linear growth. Okay, unlike your oxidation, where the material had to oxidant had to get transported through an already grown oxide, right? And the interaction, the chemical reaction happened below the already grown oxide. Here you are depositing always on the top. Okay, so there is no diffusion through already grown film in this case. Okay, so you expect the growth to be linear, because you just keep on adding. What is already there does not matter, right? But that is not true at this stage. Okay, because the surface, you are actually depositing, let's say, aluminum on silicon. Yeah, so the surface would have an influence on the initial growth. Once a closed film is formed, it's aluminum all the way. Okay, so the transition would happen only here. So this is called a nucleation delay. Okay, so many students make this thing that, okay, I have this growth curve, right? I measure the film thickness for a certain time of deposition. Everything else is the same. And I want to deposit, let's say, 2 nanometer film or 1 nanometer film. And how do I find the time that is appropriate for this? Okay, so it's easy for me to deposit a thicker film and characterize it. Yeah, so I grow 20 nanometer film, right? I do the thickness determination, and then this is my time, okay, and this is the thickness that I got. So I get a deposition rate, right? Per second, how much is getting deposited. Now I want to grow a 1 nanometer film or 2 nanometer film. Can I just say, okay, multiply this rate with 2? Yeah, that is not possible in some cases. Yeah? So you can see here practical example. Before that, these are processes where you actually stop the deposition during the nucleation. Okay, so you can then make nanoparticles. So this is about 6 nanometers in that range. Okay, so these are metal platinum nanoparticles, and depending on the substrate or conditions, so one deposition is done at room temperature. This is at 125 degrees centigrade. So you find a larger density of particles here, yeah, for example. Okay, so depending on the substrate conditions, you can have different. Here the one figure, sorry about it. There you can see on the left side. This is on silicon dioxide platinum deposition. This is on hafnium dioxide. Same temperature, identical conditions. So the substrate surface has an influence on the properties of the film that is getting deposited. So this is what I was referring to, the nucleation delay. So this is ALD deposition of zinc oxide on silicon surface. Okay, so this curve, the red one, is for deposition on silicon dioxide. Okay, so you have grown a silicon dioxide on top of silicon. So it looks nearly linear, right? It almost starts at 0, or you can extrapolate it to 0. There is still a small offset, okay? But if I am growing it on silicon, so I've done an RCA cleaning, etched off the oxide, and I grow this zinc oxide, right? You can see that it has a nucleation delay. Yeah? This is where the initial nucleation is happening. Okay. Now, if I want to deposit, let's say here, this is nanometers. Yeah, I want to deposit a 2 nanometer film. Okay, And then I did the deposition for a longer time and found the slope and say, okay, this is my deposition rate. Yeah, I may not deposit any film by just extrapolating that number. Yeah? Because it's not going through zero. Okay, many students, in experiments, you may actually find this to be a small number, and you think that it's a experimental error. I'm done, right? I know what is the time required for deposition, but then that's not happening. Okay, so you have to be very careful if the thickness is very small. The difference here is actually about 4 nanometers. Yeah, and in many cases you want to deposit films thinner than 4 nanometers.